at first stage of crevice corrosion. So again, first stage, you are having incubation. There are two equation there. One is how the oxygen combined with water become OH negative. Another one is metal plus water. It become metal oxide plus H positive and one more and E negative. Okay. Next, look at second stage. What happened to second stage? So during second stage, when second stage start is once the oxygen is completely consumed. So inside the gap, after you use up all the oxygen inside the hole, or inside the canyon, then second stage starts. So second stage start once there's no more oxygen in the space there. So elimination of oxygen inside the crevice brings standard steel to an active condition. Now, this statement tells you that stage 1, the standard steel is in active stage, in passive state. So once the oxygen consumed, there's no more oxygen in the gap there. Standard steel in that corrosion area, it will change into active condition. So you can see on this graph. This graph is an even diagram, so you should be familiar by now. Potential E versus log I graph, you should be very familiar now. Huh? If not, have to go back to previous lecture video, go and listen to the lecture again. This you should be very familiar and it's important for your coming test and exam. Huh? So here you can see that the potential change inside the crevice during the first stage and condition inside, in and out of the hole. Interstice is a hole of the crevice attack area. So we can see that there is a potential change from in into out. In into out. Okay. This line you should understand why this increased gradient here. When we discuss about the higher nobility and no nobility, and there's this graph, you've seen this graph before in the chapter 5. Huh? Okay. Now, during second stage, we know that all the oxygen was consumed, so no more oxygen involved in second stage. So what will happen for second stage? What happened to the metals? Metals itself will metal will split itself into positive charge and negative charge. So by looking at this chemical separation equation, the metals ion concentration going to increase because it's break into charges, right? So metal itself will break into positive charge and negative charge. Okay, second stage, metal concentration increase. And where does this M positive charge go? It will go and make friends with water, metal charges with water. It will become MOH, metal, this one is, I forget the chemical name for this one already, but you'll form MOH plus H positive. Okay, second stage, metal concentration increase, contribute negative charge. Okay, then what happened to the metal? What happened to a positive charge? You go and make friends with water. When metal plus water, they form MOH and they generate H positive. Second stage, you are seeing H positive. Again, pH value. What mean by if you have more H positive, pH drop. pH, the value drop, become more acidic. What happens if you increase the acidity in corrosion? Increase the rate of corrosion. This one, it increase the rate of corrosion. Second stage, you have more acidic behavior in the hole there. So pH drop to a very low value. It can drop to the pH value 2 because of chromium element in the stainless steel. We are talking about stainless steel. Huh? Stainless steel you mix with chromium. So why pH value can drop below 2? It is because of the chromium element inside stainless steels. Okay, so this is about stage 2. There's a differences between stage 1 and stage 2. Huh? Important, eh? Okay. So this one, it will go back to passivation. Outside crevice, oxygen reduction increase the alkali, therefore strengthening the passivity. What I mean by this one? This is inside the crevice, inside the crevice hole. You will see there's a generation of H positive, but outside the crevice, means stage 1, you have oxygen reduction or incubation will happen outside stage in the stage 1. So stage 1 you have alkali behavior, right? So alkali behavior, it will make the stainless steel become passive, right? So when it comes to stage 2, inside the hole, you become active stage. Okay, third stage. Third stage is when you will see the word macrocell. Right? Third stage, the macrocell current becomes stationary. So macrocell is linked with the galvanic properties. There's a positive negative charge. It will form the potential. If you plot the even diagram, E versus log I, the potential becomes stationary. What do you mean? You will see a straight line when it's straight line of the voltage when you reach stage 3. Okay, so one characteristic of crevice corrosion is that the driving voltage is expected to be lower than the pitting. So crevice and pitting, they look quite similar, right? They look quite similar, and one thing that differentiates pitting and crevice is the voltage that you measure between pitting and crevice. So crevice is a bit lower voltage compared to pitting. Because of higher ohmic drop contribution through the narrow gap. There's an ohmic drop in the crevice. Okay. This is just a guideline. How low is low? For crevice, right? Consider we take is half of the pitting corrosion. So it's about 0.2 volt. 0.2 volt is quite low lah, okay, for crevice. Okay, so rule of thumb for crevice corrosion is about 0.2 volt. So this is when we say stage 3, when it reach to stage 3, then the potential becomes stationary. You can say that once you see the E value in the even diagram becomes straight line, it reaches stage 3. And the value can go as low as 0.2 volt. Right? And in an aerated seawater, if you dip the stainless steel in the full oxygen seawater. Aerated means you have oxygen inside. The crevice corrosion rates can go between 1 to 5 mm per year. It can eat the material 1 mm to 5 mm a year, regardless what type of stainless steel you do. It will go 1 mm to 5 mm per year, which is quite a lot. It's quite a lot. If you're in the shipping industry, this one, it can destroy the shield of the ship body. Okay, let's look at number 4. Let's look at metal composition. Okay. Now, what happened in the stainless steels? Stainless steel, you have chromium and molybdenum, which is chromium, this color, molybdenum, this color, look quite similar. The nitrogen, right? Chromium, molybdenum, and nitrogen, they are good in promoting a stable passive film. Stable passive film is good for protection, corrosion protection. So that's why stainless steels, they are good. They are good for normal corrosion protection, right? That's why people use stainless steel in a normal building structure, right? Stainless steel means they are good. They do not corrode easily because of the chromium, molybdenum, and nitrogen inside there. Okay, these three form a film, passive film. Okay, this one more nitrogen. And let's look at environment factor. Environment factor, we look at 1, 2, 3, 4, 5. Factor that can affect crevice, corrode, CL, acid, temperature, potential, and bacterial activity. We have covered the corrode, acidity, temperature you've seen in previous chapter, potential, we just mentioned just now, the voltage, right? Bacterial activity. Why bacterial activity can contribute to crevice? What is the product when microorganisms they have activities and life form? They will generate acidic products on the surface and trigger this component. So what factor that trigger corrosion, crevice corrosion? This, and this. Okay. So we have two picture here. What does this two picture is that these two, they are the same. Okay, this one is stainless steels. Stainless steel, they dip into the same environment, right? They're in the same environment. This one, they form, they join the stainless steels and stainless steel, this one, stainless steel 316, this is also 316, but they join the 316 with another metals. There's a different metals joined together. Okay. You can see the results when you join two different metal together. This one still have crevice, but this one more serious condition happen. Okay, the crevice condition when you join two different metal together is more drastic compared to individual stainless steels. Why? You know that when you join two metal together, you will have galvanic corrosion inside there. Right? When you have two metal joined together, metal will fight for nobility. One go higher, one go lower, and they will trigger the exchange of electron. Right? So in the previous slides, you see there's a usage of electron there. So when there's an exchange of electron, corrosion is going to happen. So this is just a example of how crevice can happen. This is on the surface. If you look deeper using microscope, you'll see there's a tiny hole on the surface. This is just on the naked eyes or normal camera photo. Both exposed to seawater. Both are exposed to seawater, and you can see what happened to them. The rest you can read on the slides. Time of exposure is 6 months for these two photos. Exposed to 6 months, and you can see this one, the crevice attack is 0.5 mm. The second one show no corrosion and formation of some carcass deposit and consequences of galvanic coupling of carbon steels. So this one, if you join two metal together, galvanic corrosion take over, and it will wait. Right, galvanic corrosion will take over. This one don't happen galvanic corrosion. So crevice going to look for tiny hole to attack. This is a difference between the two scenarios. Okay, so all these are carcass. So this word appeared in a chapter when we talk about seawater corrosion. Right. Next, we look for prevention. How we prevent? I give you all. First, more basic one is that you change the design. You change the design of your devices. For example, the heat exchanger. You know that crevice will look for the exposure of these 5 factors, right? 5 favor that trigger the crevice. Correct content, acidity, temperature, potential, and bacterial activity. What mean by design? How you prevent by design? Meaning, when you design, you look for the area that have the possibility to expose to that 5 element. You reduce the exposure in your design. For example, this is the heat exchanger, and the red color one is the hot air with its high temperature. Blue one is the cold water to cool down the heat exchanger here, or to have the exchange of heat over here. All right. So what you do is that you cleverly design the way the water, the cold water and hot water bypass. All right. So that the crevice do not appear in those high temperature area. Okay. So for example, heat exchanger used in the ship, they will pump in the seawater for the circulation of the heat exchanger. So you know that seawater have chloride element. So you try to avoid most of the part get contact with the seawater. You only allow a certain portion of the devices or tube containing the seawater. Okay. All right. Okay, so beside design means you look at the flow of the crevice, right? Another one is you select a resisting material, or you use cathodic protection, right? You use a cathodic protection in crevice corrosion, right? In the case of standard steels, iron anodes often used. This one, cathodic protection, is the one that we show you just now. Okay. When you join standard steels and metals, galvanic happen, take over, and it will not allow crevice to happen. This one happen without galvanic. Crevice happen as deep at 0.5 mm. So one of the way to prevent crevice, you use the concept of galvanic corrosion protection. You use cathodic protection in your scenario, cathodic protection, or you use crevice resisting material. Okay. Next, we look at Crevice-Like corrosion in active metals. First, we look at corrosion under insulation. So when you insulate a surface, means you cover a surface, right? You have this is a very serious matter. When you insulate a cable for underwater cable and all this. So crevice will look for the tiny hole between the insulation layer and the metals. You go and attack all these small area in the cover, right? So there's often a high chloride concentration in the marine environment. So insulation, usually here we talk about standard steels and seawater. Here we talk about equipment that in the marine atmosphere. Why marine atmosphere? It linked with the seawater. Seawater have what? Have high chloride concentration. Then crevice can happen. So this is a schematic diagram for the seawater. So there's exchange of ion and chloride between the steel and phlegm. So previously, before the break, we already discussed first stage, what happened. First stage, you have a passive phlegm over there, and you have incubation, you have oxygen depreciation happen, and so on. Second stage, you have creation of acidic products, and so on. Third stage, you reach a constant potential, right? So this is just a schematic crevice corrosion in seawater. So oxygen enter through the air, through the water, seawater here. And then you have a shield, then crevice going to happen over here. Okay. So metal will break itself, right? Metal will break itself into charges. When they break, some gap going to happen, and then they will become deposit, they will become oxide over here. Right? So sometimes they also carried by rainwater. Okay, the where is all these pollutant can happen on the marine equipment because of the rain. When you travel in the open sea, it rains. The rain will capture the pollutant in the environment, and then the rainwater will reach to the marine equipment. Then crevice will happen. Okay. So in beneath the insulation. So why you need insulation? It is because you below the insulation layer there's a hot temperature there, high temperature below the insulation layer, right? That's why you use insulation layer, because you want to insulate the heat element. So when you insulate the heat element, there's a high temperature there, right? High temperature there, and then you expose to water, then leading to high correct concentration, Cl negative and so on. Yeah. This is on a marine environment under insulation. Okay. Another one is automotive related corrosion. All right. Sadly, last few weeks ago, Malaysia have the very serious flood condition. Loss of personal properties was destroyed because of the flood water. There's on a news or in a newspaper, you see a loss of cars was submerged in the water. So this is going to be generating automotive related corrosion, especially crevice corrosion. Where does this crevice corrosion happen? It is in the hidden parts in the car chassis, especially made from the metal seals or steel sheet. So this is an example. Right, these are metals that exposed to the water, and crevice going to attack all this area. And just now before the break, we also give you a 5 diagram there, right? So how crevice can happen, right? So one of it, as long as there's a hole between the metals, then crevice will go and attack that area. They attack the joint, they attack the sheet overlapping. If there any spot or is there any welding spot there, they're going to attack all this area. Okay. So corrosion in the hidden parts is called in-out corrosion. It still fall below crevice corrosion, but for automotive, when you send a car to inspection in the Puspacom, sometimes when they inspect your car, they saw some corrosion parts inside there, right? So maybe your car was in the flood area and was submerged in the water for so long, and then you plan to sell the car, you need to get a permit from Puspacom to check your car and certify your car is fit for the new user. So they will go and check if there any damage in the car. If they write this one, in-out corrosion, means they found a hidden corrosion inside a certain area of the cars. Some junction, bonnet, and all this. As long as they are made of the overlapping of two sheet metals, then crevice will happen. This bonnet and so on. One of the reason why all these area can expose to crevice, right? Because sometimes when they do car production, some of these parts, they are not accessible to painting production. When you produce a car, there are few layer of paint before they send to the end user. In a car production, they have a few layer or few procedure in painting. They'll paint the first layer, then second layer, third layer, then the protection layer, and the final layer of the the paint. You can go for Google and watch video for how they do car painting or how they manufacturing a car, right? So these are the strategies to neutralize the corrosion. There are 3 ways in automotive. 1, you improve the design. 2, you look for the trap in the design and reduce them, or you simplify the rivet hole or the how you join the 2 metal together. All right, and you adopt galvanized steel sheet in the car design. Okay, this is a selection of material. Okay, improve design, reduce number of traps, and highly recommend to use galvanized steels in the automotive design. This is a video about rust protection features. Okay.
As a vehicle ages, the effects of humidity, water, road salt, and other environmental agents can take a destructive toll on metal components in the form of rust and corrosion. Toyota vehicles are specifically engineered to prevent this sort of deterioration brought on by the harsh road conditions of the Canadian climate. Chemicals used to de-ice roads are especially harmful to vehicle bodies, so Toyota engineers work hard to battle corrosion right from the earliest stages of the manufacturing process. Rust protection at Toyota's manufacturing facilities starts before the body shell is even painted. The body is built of numerous panels which are made of high-quality materials specially treated with rust-resistant treatments and coatings. Before the painting process begins, the body shell is cleaned and all finishing processes take place in a spotless, dust-free environment. Vehicle bodies are first chemically treated to protect exposed metal. A chip-resistant urethane primer is applied before painting, followed by a 2K clear coat after painting for superior scratch and chip resistance. Paints and clear finish coats are applied electrostatically to ensure a complete and even coating of protection. In some vehicles, over 70 meters of PVC sealant is applied to panel joints and seams to prevent the accumulation of moisture. Each vehicle goes through a full inspection of the underside PVC sealing process to ensure complete seam coverage. Heavy-duty stone guard material is applied to the underside of the body, protecting vulnerable components from damage, and wax is sprayed into crevices inside the body and door cavities to seal them against the intrusion of water. Stainless steel used in exhausts and aluminum radiator cores also help prolong the longevity of these parts. Plastic and felt fender liners in wheel wells and protective films on body surfaces help guard against stone chips, which can expose bare metal to the elements. Building a long-lasting vehicle is taken seriously, and Toyota offers a 60-month unlimited kilometer corrosion perforation warranty on vehicles. Toyota regularly performs destructive testing on vehicles to confirm that the manufacturing process meets all company standards for corrosion compliance. This involves complete disassembly of sample vehicles and examination of even the most minute details to spot defects so that they can be remedied if a problem is identified. Having vehicles which can resist corrosion and survive the harsh environmental conditions in Canada are a vital part of building vehicles renowned for their quality, durability, and reliability. Toyota's efforts to build long-lasting vehicles are reflected in the many awards and accolades bestowed upon the brand. For 2016, Toyota recently won 6 first-place finishes in the Canadian Blackbook.com Best Retained Value Award Series, 3 more than any other auto manufacturer, with the Tacoma and Tundra holding their class-leading position for the 7th year in a row. Toyota also came out on top in the ALG 2015 Canadian Residual Value Awards with 10 winners, twice as many as the next closest automaker. For the 7th straight year, Toyota took the Reader's Digest Most Trusted Brand and won a 5th consecutive Most Trusted Hybrid Manufacturer accolade. While Toyota vehicles offer outstanding protection against corrosion, it is important to note that regular washing of the body and undercarriage, especially around the wheel arches, can help prolong the life of your Toyota for many more years of service. The features and functions described in this video might not be applicable to your specific Toyota model. See your owner's manual for details. Thanks for watching this Know Your Toyota video.
Okay, enough for the free commercial for Toyota, but you can see how they in the automotive industry, how they change the design, how they change the material, how they change the manufacturing process for rust protection. So next we look at a reverted structure. We have seen on 3 structure. Okay, we have seen 3 examples. One is the boiler, right? Insulation, corrosion under insulation, automotive, and now we look at Revert structure. Okay, so Revert can form a hole or gap between the plates and the Revert itself. So I hope you know what is Revert. By now you should know what is Revert. So when you Revert something, there's a hole between the board and the metals that you want to join together. When there's a hole or gap, then crevice going to attack that area. So you can see all these Revert area. This one also is a layer of metals, and when they have layer of metals, there's a gap, then you will go and attack all this. Revert also. Okay. If you want to read more about how crevice corrosion happen in the Revert or boating, you can go to these journals to read the remaining details. These photos I extract from these journals, published by Hennemeyer in 2011. Right, the influence of Revert corrosion in the durability of Revert connection. Published in Steel Construction, Volume 4. Okay, and this is a DOI number. Okay, so we have introduced you Crevice-Like corrosion in the active metals, and then we go for a few more slides. All right, then we conclude chapter 6. So you are familiar with filiform corrosion previously, and in fact we spent 1 chapter to explain filiform. So for the crevice corrosion, there's one type of you can say filiform is fall under crevice corrosion, right? You have seen how filiform can do, right? Previously I showed you some video about filiform. Usually filiform, they form under paints or protective layer, right? They have a movement of the filiform and so on. Yeah. So you can see all the scratches below the paint. This. So what control the filiform corrosion is the humidity. Yeah. So you have seen this diagram before, right, in the filiform chapter. So You should be familiar with it. Huh? So this is a video of how Filiform on an aluminium alloy. As you can see, this one was fast forward. As you can see, the black dot is the high potential energy. So you're going to going outwards of Filiform. Okay. So we have discussed quite detail about Filiform in the previous chapter. So we're going to jump to the next one. So 6.9 applicable standard. This one you have all the lists in your tutorial handouts, right? So you have ASTM G48, 78, 192. You can read lah. Okay. Each one is targeted to individual different material. For example, G48 is for standard steels and alloy, published by American Standard for Testing Material, ASTM. That's why the word ASTM is there. ASTM stands for American Society for Testing Material. Okay, you should learn this one during your material module. ASTM. G48 is for standard steel. And if you are doing your FYP that related to testing method, then you refer to ASTM G48 if you test on standard steel and related alloy. There's a certain standards for each material testing method. Another one is for crevice corrosion testing. If you want to publish data about crevice corrosion testing for iron-based, nickel-based standard steel, then you refer to G78 and so on. There are different types of test method there. You have all these in your tutorial handouts. So first one, 48, 78, 192. Next one will be 764 is on the surgical implant material. This one is important for medical devices. And they should show you when you want to sell the medical products, especially for surgical purpose, implant purpose, they will come with a certificate of ASTM F746 data. Right? Beside ASTM, you also have two ISO example. International Standard Organization, ISO. Okay, ISO stands for International Standard Organization. 18070 is for crevice corrosion specimen, especially standard steels. And 18089 is for determination of CCT, the temperature for the crevice temperature for standard steels. So you have the list is quite long. So this is just a few standard that we use, especially when it comes to crevice corrosion. It's important because this is part of your learning outcome. You should know what are the standard is there. You should able to give a few example of standards when it comes to corrosion control and prevention. Okay, so I give you a few examples. In a test, I will not expect you to give all, but at least 3 of the standards. Okay, and then you explain about the standard. What does it mean? Okay. So with this, we conclude chapter 6 today. All right. So we will go into chapter 7 in our next lecture. Okay, let me end the recording.